All right, welcome. In this video, I want to continue in sort of the theme that we've been doing with algorithm analysis. But now what I want to do is I want to take all the pieces that we've looked at in the last several or even dozen videos and put them all together and use them to do analysis on an algorithm. Again, another one that we might already be aware of, which is the bubble sort algorithm. And I'm not going to do that all at once. I'm going to do that in a couple of videos as well. But we're going to start, at least in this video, by taking a look at the bubble sort algorithm and then trying to prove it correct. And now again, this might be an algorithm that we're already comfortable and familiar with. But largely, maybe up to this point, the way that you sort of proved this correct is what we would call empirically, which is you just gave it a list and you said sort it, and you looked at the output and the output was sorted, and then you did that 5 or 6 more times or a dozen times or 100 times, and you said to yourself, hey, it looks like it works. Or maybe you even did some rigorous testing on it, but no one's going to be able to test it on all infinite possible inputs. So the reason we do a proof of correctness is to replace that empirical test, which can go wrong sometimes, with an analytical proof of correctness that will basically argue for us that at least if we've implemented things properly, this algorithm will always properly sort your list for you, which is of course our goal. So that's what I want to do. Again, you may be familiar with bubble sort already, but that's actually quite good. That allows us to at least lean on that experience that we already have. Okay, so before we look at the algorithm, of course, as has been the theme so far in this series, we'll look at the problem first. And the problem that we're facing is the problem of sorting a list. And here, at least, is very common in computer science to abstract away what kind of list we're looking at. It's a list, as far as we're concerned, of integers. And if it's not a list of integers, we'll just relabel whatever it is in the list with integers, and we'll now talk about the list of integers to make things easy on ourselves. Okay, so as our input for this particular problem, we're going to have a list of integers. In this case, I'm calling it a sequence, to borrow the sort of more formal mathematical definition of a sequence. I've got it sort of, I'm using sequence notation here with these round braces to show that this is a sequence of numbers. Now in math, we sometimes use another term for sequence. Maybe you may have heard of vector, or you may have heard of a tuple, an M tuple sometimes we call them, or M tuple, which follows sort of the naming convention of double, triple, and so on until you get to too big a numbers that I don't know what the names are, and we call them M tuples. Or if they're small, as I mentioned, we sometimes call them doubles or pairs or triples and so on. And so there's lots of similar names, and usually we switch from one name to another depending usually on our purpose. What are we using it for? And in this case, we're talking about a more computer science-y purpose. This is the purpose of displaying it in a problem. And so usually in a problem, sequence is the formal mathematical object that we're looking at. Not necessarily a set, for instance. Remember, a sequence is an ordered set, okay? Just again, our mathematical formalism sort of creeps up here and there to really just fill in the gaps to make things a little bit easier to communicate by this word sequence carrying with it a lot of mathematical power. Okay, let's continue. So that's the input. We get a sequence of integers. In this case, I haven't really highlighted it, but again, we'll say that list is of size n being unstated here, a variable. Okay, what's our output? Well, of course, we expect if we're dealing with the sorting problem, our output should be the list sorted. But saying that, putting that here would be quite informal if we just said the same list sorted. So instead, what I've done is I've gone ahead and I've again borrowed a powerful mathematical word here, the word permutation, and I've used it in the definition of my output. Here I say the output should be A prime, a permutation of A. Okay, that alone, that phrase or expression alone carries a lot of power. I'll get to that in a second when we look at this definition here, but this is a permutation of A. I think a lot of us know what permutation means, such that what? Such that in A prime, that's what I'm highlighting why I've put primes on all these A's here, A prime of 1 must be less than or equal to A2, A prime 2, and so on, A prime all the way up to A prime of n. And so this sequence that we've defined here is ascending order, right? So the equalities means we might have some ties, but if we assume there are no ties, then this would be in increasing order or ascending order. And so basically what we're asking for as our output here is the permutation is saying what? As it says down here, basically reorder them such that they're in ascending order. And of course that's basically a more formal version of what we said before, which was, well, we want the same list sorted. This tells us a bit more. What sorted means, it means a permutation, and in what order, we didn't specify that in our more informal wording. Here this is saying ascending order. And notice here, we could have also said descending order. That's just a different problem, but it's not really a different problem. It's just the same problem. It's just asking us to put it in the reverse order of this problem. So when I say it's the same problem, I said two things there. I said it's a different problem and it's the same problem. So which is it? Is it a different problem or is it the same problem? Well, it's actually a different problem, because sometimes we want things in ascending order and some things we want them in descending, and that matters. If I ask you, please give me something in ascending order, and you give it to me in descending order, that matters. But the reason I say it's the same problem is because if I could solve one problem, I could solve the other. And that's the way we engage our computer science brain, or problem-solving computer science mind, is saying, hey, I don't want to solve the same problem over and over again. If I've solved it once, how can I use it to solve other similar problems? And that's the idea here. That's why we abstracted away to just integers, and that's why we're only going to be worried about ascending order, because if you have a sequence of something else, or you want it in a different order, you can solve it in the same way as this, so you don't have to reinvent the wheel. Okay, what have I left out? Well, what is this business about a permutation? So here I've got a definition saying a permutation of a sequence, or we can apply it to other things like sets as well, are the same elements of the sequence, but in a different order, potentially. We could leave it in the same order. If we gave you a sorted list, we want you to just leave it alone and give it back to us, right? But the mathematical power that comes with the word permutation is that it means different order. Same things, different order. Okay, so really it carries with it the power, two properties. Okay, and I want to highlight these two properties here. All of the elements of the original sequence are there. We haven't left any of them out. Okay, so this is what we might think of as the no missing elements rule. Permutation, when we say a permutation of a list, we mean don't leave anything out. The second thing says, well, don't put anything else in. Including duplicates. Don't put something new in, don't put in a duplicate, no extra elements in. Only, all and only the elements that were in the original list. And that all and only clause is really important, it's critical. And the reason we bundle it into this word permutation is so that in mathematics, when we're talking about stuff like this, we don't have to spell all this business out. We can just say a permutation, and then all the other mathematicians in the room go, oh, I know what a permutation is. That means all and only the elements, but maybe in a different order. Okay, and so this is, and I think most of us listening to this who are familiar or have heard of a permutation before are like, yeah, I knew what that meant. That's why we use these words. Okay, so all the time that we're formalizing in these videos and in any of the other videos in my series, it's so that we can simplify our communication to one another and use these sort of formal mathematical terms to carry a lot of communicative power. Okay, so that's what permutation is. It's one of my favorite mathematical words because it carries so much behind it. I can bundle a whole bunch into one word. Sometimes I think of this as like being able to be clever in programming and get one real powerful line of code that does like a whole bunch of cool things all on one line. Sometimes that's not good, right? But the idea is when you do that cleverly, it's sort of like bundling a good mathematical definition into a term. Okay, so we've sort of looked at the problem. The problem is sorting. My last little point here is that sorting a sequence of integers, or sorting a sequence of anything, is a central problem in computer science. And it's so central that before you got to this video, you've probably heard of it before now. And even before that, before you even thought about computer science or sorting in a computer science sense, you probably had to sort something sometime in your life, which means you've probably already had to solve this problem in a real practical way, just sorting cards or sorting, envelopes, whatever it might be, in your own life. And so you probably already have a sorting algorithm built into your brain, your little brain computer that's already known for doing some pretty cool algorithmic thinking. So you've probably already got one in there. And then maybe more formally, that if you play cards a lot, and I know I played cards a lot when I was younger, you actually develop explicit sorting procedures in your mind. You think about it, you say, hey, now I'm going to do this thing, and now I'm going to do this until your cards are sorted, or whatever it is that you have to be sorting are sorted. And so as a result, this problem is very well studied, and there are several well-known algorithms. Just like I mentioned, maybe before you even thought about it in a computer science context, you thought about sorting. Well, that's the same thing that's true for humans. Before we had computers, we still had to sort things, and so we've been thinking about sorting for hundreds of years, thousands of years, certainly. And whether we've been writing them down as algorithms or not, we've definitely been developing them as algorithms. So even some of our more interesting algorithms like quick sort or merge sort likely were carried out physically by individuals long time ago, not knowing that they were doing an algorithm per se, but they knew that if they did it, they'd end up with the output that they were looking for. And then other algorithms, like sort of like a bucket sort type of algorithm, are actually developed from physical algorithms that we might do. And for that matter, so I would say our selection sort and insertion sort, at least I think of them as the two ways I usually sort my cards when I play cards in my hand. That's very natural human ways to sorting. But this video, we're going to talk about bubble sort. And bubble sort is really designed for the machine. It's designed to think the way that a machine thinks, not necessarily the way a human thinks. And the reason we have to do that is humans are incredibly powerful computers. Our brains are quite powerful. One way to think of it is we have a large number of registers in our brain, which means at one point in time we can keep in our mind a lot of things. So if I look at all the cards in my hand, and maybe there's 10 or 13, depending on what kind of standard game I might be playing. If I look at that, I can take those all in and think about them all at the same time. In a sense, that means I can hold them all in registers in my brain at the same time, which means for me to pick out the smallest one is almost simple. With about 10 of them, maybe around 10 is what we know as humans is around our limit to sort of hold in our mind. But if I have 10 things and I'm looking at them and I need to know the smallest, you can usually just do that automatically. And when I say that, I mean our brain will be able to do it so fast we don't really think about it. It just can see them all and go, that's the smallest, the 2, whatever it is, okay? But if we have more than that, if we have like 100 or 1,000 things, now we can't look at them all at the same time. And that's kind of like how a computer operates. A computer can't hold all the numbers in its brain all at once and then just pick out the minimum. That's not one of the powers that it can do. What it can do is hold 2 elements in its brain, in its central processor, if you like, at a time, and it's 2 registers. I mean, it can have more registers, but ultimately it can only compare 2 of them to see which one is bigger or smaller. And that's going to be the foundation of our algorithm bubble sort, which is if we're a machine that can only look at 2 things at a time, the most limited, and compare them, then how would you sort that list? So imagine it's the same as the idea that I said, but now imagine being visually impaired so that you can't actually see all the cards all at once, and you have to look very closely at each card one at a time before you can compare them. That limits the operations that you would be able to do to do your sorting operation, and so you might need to use different types of algorithms. And that's what I want to look at next. Let's take a look here at the bubble sort algorithm that at least that I've got here written in pseudocode. Okay, now one of the reasons, again, I've written it this way and I've written it in pseudocode is because on an algorithmic standpoint, we're not really thinking about the implementation specific stuff that you're doing. Maybe you're writing this in Java, maybe you're writing it in JavaScript, maybe you're writing it in Python, some other language. The way you implement it from language to language are going to have changes in how you will implement it, but ultimately the structure of all those implementations will be the same. They will have this type of structure. Now, the second choice that I make in writing this code was anticipating what am I going to use this code for? What is the purpose of this bubble sort algorithm that I've written? And even in pseudocode, even algorithmically, there could be multiple purposes for this code. One reason I might have this code is just to communicate to implementers. Maybe I'm developing some code base and I need someone to write a bubble sort algorithm for me, and I ask them, hey, can you write that bubble sort algorithm? Here's some pseudocode for it. Maybe the only purpose is to give pseudocode so someone could implement it. If that's the purpose, then any pseudocode that suits that purpose is good. And that maybe depends on what language you're going to write it in. Okay, for instance, maybe your language doesn't have for loops in it. If it doesn't, then this is probably not very good pseudocode for it, right? Okay, maybe you're stuck in a recursive language or one that has more primitive looping structures like just while loops. In that case, different pseudocode might be better. But the purpose I've put this pseudocode to is I want to analyze it. I want to prove it's correct, and I want to count how many operations it carries out. Now, because of that, I've made a couple choices. One, I don't want to do a lot of extraneous operations or extra clever steps. Anytime I introduce a clever step or something cool that might, early termination, checking to see if I'm already sorted, something like this, all that does is increase complexity in my algorithm, which increases the complexity of the proof of correctness that I end up having to do at the end. And it also adds steps in so that my runtime analysis, which is the second purpose I have here, is also overcomplicated. So because my purpose here is analysis, usually what that means is you want to start at least with the simplest version of your algorithm. Okay. The only time I would say when you would step away from that is when the simplest version of your algorithm is not the most efficient version of your algorithm from a runtime perspective. Okay, usually they're all correct, so you want to prove them all correct. But oftentimes, say maybe this way is not the most efficient because we don't use a clever data structure in there. Okay, well then often what we would do is we would analyze this version, the naive version we might call it, and then afterwards we would reintroduce the complexity because it's a complexity and we don't want to deal with it all the time. We'll introduce it after and say, okay, say we want to improve this and make this sort of subtle extra improvement. We'll introduce this complexity, add an extra layer to analysis to show that yes, the complexity still works as desired, but you don't need to use it. Not always do you want to use those extra improvements. Sometimes they're not necessary. In this case, we don't have an extra improvement other than that you can add an early termination to bubble sort. Okay, and if you go look at other implementations of bubble sort, there is an early termination, which is at this step here, we're making a swap if we keep track of our past, and this is getting a little bit ahead of ourselves, but some of you, I think most of us probably have already encountered bubble sort before, but at some point later, if after one of these passes we've never made a swap, that means we've never found two elements that are out of order. If we've never found two elements out of order, that means we're in order, we're done. We could early terminate. But adding that extra bit of checking, an extra flag in here, an initialization of the flag, checking the flag, or setting the flag, checking the flag down here, and early termination, adds several extra lines of code, pseudocode in this case, and really it doesn't really gain anything for me in my goal to prove this correct. It's just a clever early termination bit. Ultimately, if I need that to argue that for its best case running time, sure, I'll introduce it, but that's what I mean by extra sort of complexity. I'm going to leave it out here. Okay, let's just make sure we know kind of how the bubble sort algorithm works, because here in a second, we're going to be trying to prove that it's correct. All right, so let's just go through and look through the idea. Now, we've got our input as we've stated up above here, and we've got two nested loops here. All right, the outer loop, we're going to go from, we're going to index it with I. Now, usually when I have two nested loops like this, my instinct normally is I, J, and K, and so on. Okay, that's what I labeled them. That's sort of the convention in computer science. All right. I also, if I want to keep track of this, I'll usually use I's for N's and J's for M's. Well, this is just N and N in this case. Okay, so we have no M. Although in this case, what we do have is for our upper bound, you'll notice I stop one early. Now, why is that? Well, the reason is in my code here, I'm going to be making comparisons from a term to its next term. Okay, to its next term. And so what I don't want to do is get one of those sort of out of bounds calls where I'm actually looking for term n plus 1. So you've probably noticed this in your own implementations, that usually we're going to stop one early because we don't want to do that last comparison where we compare the last element to something out of bounds. Okay, so that's why that one stops there. Now the other thing here is this outer step here, sometimes you can run this all the way to the end as well, n minus 1. That's a more naive implementation. Okay, so why didn't I do that? I just argued earlier, why not just use the simplest implementation? Well, here actually, I think making it more naive doesn't actually help my purpose here. It actually makes things a little bit more complicated on the proof of correctness. So I'm definitely going to leave this in as it is here. Now, why is that, if you're sort of interested, is that this version is going to stop right when we've moved the right element into place. If we leave it up to minus 1, leave it all the way to the end, then what we're going to do is a bunch of useless checks where all those elements we already know are in the right order. And so usually we leave that out of our actual implementation because that's wasted effort. It's not necessary. And then also I'm going to leave it out of my analysis here so we don't have to deal with that in our proof of correctness. Okay, so that's why our upper bounds are a little bit different. Okay, instead of going up to n minus 1, we go up to n minus I. Now let's comment a little bit more about what that means. That means the first time, the first loop of the outer loop, our I is 1, so we go up to n minus 1. So we really do go to the last element, like I mentioned. That's good. That last check will then be n minus 1 and n. Okay, good, safe, no out of bounds, right? And then what we'll see, what about the last case? The last case, we get n minus 1 plugged in for I here. That's n minus 1. That's just 1. We only get j from 1 to 1. We only do it once. We look at the first element and the second element, and if they're out of order, we swap them and we're done. Okay, so what does this actually do? Well, here's what we need to prove. Okay, our goal in our second is to prove this, but we need to argue that, you know, I sort of hinted at this already, but let's work outwards a little bit then and see what does this do. Let's imagine we don't know how bubble sort works. Let's see how it does. Well, this inner line says, I've mentioned it a couple times now, if the two elements are out of order, okay, remember this is the order I want them in. Now, the lesser indexed item should be less than or equal to the higher indexed item. But here I'm saying if the lesser indexed item is greater than the higher indexed item, that means they're out of order. So this is basically saying if we're out of order, swap them, put them in order. Okay, so the central part of bubble sort, remember I said our computer is a little bit vision impaired. It can only see two at a time. So it looks at one and it looks at the other and it compares them, and then it says if they're out of order, swap them. And then it maybe puts them down and picks up the next two, okay? And that's exactly the idea here, is that in bubble sort, we're gonna go, this inner loop is gonna loop through all the elements, going left to right in our list, and say, A1, A2, are you out of order? No? Okay, leave alone. A2, A3, are you out of order? Yes? Okay, swap. And so on until we get to the last pair, and then we rewind back and we do it again because we do this loop over and over and over again. But the next time we stop short, we stop short, we stop short until the last time we do it, as I mentioned earlier, we only compare these two and put them out of order. Okay, so how do we know this works? How can we be certain this works? Well, of course, as I mentioned before, empirical tests, maybe we sort of trust in the power of algorithmics and we plug it in and see that it works, or we try and argue that it works. So here's where I want to, again, sort of, we went through and argued what it was doing. Now we want to argue why is it doing that, okay? So here we see what I sort of want to pull out here is that we have two loops. The way we were proving correct before is we proved a loop invariant. Well, with two loops, that means there are two loop invariants. And with two loops, that means if they were sort of side by side, these are nested. If they're side by side, we could do them separately, but because they're nested, one of these proofs is going to depend on the other. In fact, sometimes they both depend on one another. Okay, and so usually, just like in the analysis cases, usually to start on the inner one because it's more isolated. And then once we've finished proving how the inner one works, we can step out to the outer one, prove how it works, and then step out one more time and prove the whole algorithm is correct, or the whole algorithm is correct for our problem. All right, let's start with a very simple list like this one here. Okay, that way we can follow through, and we can also verify our loop invariants with an example. This is a proof by empiricism. This is just empirical proof too, right? But that proof by example can inform how we do our analytic proof in a second. So the first bit is we're going to do the inner loop. Now let's maybe pick a few values here. So let's go, this is 1, 2, 3, 4, 5, 6. So that means our n in this case is 6. And we can kind of trace along with our loop over here. If we really wanted to, we could do each step I equals 1, dot, 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 dot. Although that might be a little bit tedious, let's instead just sort of look at what's going to happen. So we'll start with maybe I equals 1, and we'll have j equals 1. Okay, we'll start with our j equals 1. And in this case, we go j equals up to n minus 1. That's our final position, which in this case, n minus 1, if n is 6, that looks like 5. Okay, that kind of makes sense. We're going to go 1, 2, 3, 4, 5. That's one loop. Now, what we're trying to do as we do each iteration of this loop, I'm going to do the j loop, is I want to identify, or at least I want you to try and identify as we go, what the loop invariant is. What property of this list remains true after each iteration. There's going to be a few different properties that are true. Remember, which property do we want to focus on? One that might help us prove this correct. So again, what might help us prove it correct? Well, we're trying to argue at the end that these are in the right order. Okay, well, what things might help us argue that they're in the right order? Well, we might need to know the rank. You mean the smallest one, 0 is the minimum, 7 is the maximum, and based on the rank, you're supposed to be in a position, right? 0 should be in the first one, 7 should be in the last one, if we were sorted at the end. So the things we want to focus on as we're moving along here, if we want to identify our loop invariant here, is the rank of our elements and the position of our elements. And while we're doing it, being conscious of I and j, because whatever property we're talking about is probably going to be dependent on at least one of these, we'll keep that in mind as we go. Now, let's do the first step. The first step is 2 and 7, and it does a comparison over here. If the 2 was greater than the 7, we swap, but it isn't, so we leave it alone. So after our first step, I equals 1, we go into 2, we leave it alone, but now we're here, our j is here, okay? Now we compare our 7 and our 3, and we do find that they're out of order. So they end up getting swapped, okay? Again, one thing I want to focus on here is the 7, because the 7 has moved here. Okay, remember, one thing that we do on each of these swaps is we look at the two elements and the bigger of the one moves to the right. Well, at the same time, j moves to the right, so in a way, what we're doing is we're taking that biggest element along for the ride. And let's look again at the next step when we do 7 and 4. Indeed, 7 is greater than 4, so they're out of order, so we'll have to do a swap. There's that biggest element again in that position as I said, it's sort of going along for the ride. Okay. Now, I'm gonna use two phrases that I think are going to be important. That number 7 there is the maximum. We know it's the maximum, but it's not just a maximum, it's the maximum so far. Again, sometimes when I want to think about this and I'm working on a problem like this, I say, well, squint my eyes a bit. Maybe this list isn't all of the list. Maybe it's 100 long and I can't see the other elements in the list. Well, the 7 is the max, but it's the max of the list that I can see so far. Maybe just these 6 elements. Maybe when I see ones down the road later, I'll find 100, and 100 might be bigger. Okay, so one of the phrases I'm going to keep my eye on, again, this is going to help me maybe characterize my loop invariant in a second, is the max so far. And this is still informal. Okay, I might need to formalize that. What do I mean by so far? Max is not so hard. That's one of those math words that carries some power with it, right? Maximum, we know what that means. But so far, what do you mean by so far? That's where the j is probably kicking in. Okay, because I'm on loop j. Okay, let's just go the next few steps because I want to see what happens at the end of all my j's when I get to 5. Okay, so let's do the next 2 steps a little bit quicker. First, 7 is greater than 0, so they'll swap. But then it's also greater than 1, so we'll swap there as well. So after all those steps, the 7 ended up here. Now, this is probably enough analysis for us to identify the 2 loop invariants, if we're clever. I mean, I've seen this one before, I'll be honest. So I kind of know where we're going. But I think some of you might already notice here, at least if in this informal sense of the max so far, that after this whole pass, the maximum element of our list, at least the one in our example list, 7, has reached the highest rank, which is its home, where it belongs. That's the right spot for it in the sorted list. You'll notice our other numbers, 0, 1, 2, 3, 4, they're not in the right order, but the 7 is where it belongs. Okay, it's where it belongs in this example at least. Okay, so in a sense, what I've just characterized is the outer loop variant. After one iteration of the outer loop, so that was iteration 1 we just carried out by hand, right? So after iteration I equals 1, the maximum element, in our example case 7, is in the right position. Or another way of saying that maybe is, after one iteration of the outer loop, we've put one element into the right position. Which one? The maximum element. So maybe if we want to characterize that outer loop invariant, what we're trying to say is that the outer loop is, or sorry, after an iteration I of the outer loop, we've put the I highest elements into position. Okay, so after the first one we put the maximum element. After 2 loops we'll have the 2 maximum elements, and so on. And in fact, we can probably verify this ourselves if we just take a quick look. If we do the next pass, no switch, then the 4 is going to float up something like this. We're going to get the 1 in here and the 0 in here. After the second pass, when I was 2, we'll have the 2 maximum elements up here, and then the 3 will float up, and then the 2 will float up, and so on. So after each iteration of the outer loop, we have put another element in its right position. Okay, but let's go back to the inner loop. The inner loop is telling us, remember, we rely on the inner loop to prove the outer loop. So what's the inner loop doing? Well, that's where this max so far is going to come in. The max so far is in the right position so far. So it's in the right position so far. Now this is the interesting part too, because what we were arguing up here for iteration I is we said something like the I maximum are in the I right positions, right? Notice that this phraseology is almost the same as this one, except this one has the so far clause. What that sort of means is when we're done the inner loops, when the so far reaches the end, when so far is good enough, we get this property, that the maximum, not just so far, but of the whole list, is in the right position, not just the right position so far, but of the whole list. Okay, so we just need to take these kind of ideas and maybe characterize them a little bit more formally, and then let's just do that again back on the slides. All right, so here we're starting with the inner loop invariant, and in this case I've already characterized it, but what that means is I've sort of taken that phrase so far and I've cached it in terms of J. That means I've just defined that informal phrase so far by saying, well, what did we mean by so far? We were really just talking about iteration of that loop. Which iteration? Iteration J, because we were using J in the inner loop. So let's just take a look at the way I've phrased it here and see if it makes sense in our own logic checker in our own brain. So here it says, after iteration J of the inner loop, okay, that was the loop we were talking about, the maximum element, okay, we got that phrase in there, maximum, because we were talking about the maximum so far. Well, now what we need to do is characterize what do we mean by so far. Well, that's where we need to bring J into the equation. So here we're saying the maximum element of these elements. Now we might have to double check that this is exactly what I mean. Did we really mean of these elements? Okay, is in position J plus 1. Well, maybe let's go back and say, well, remember here, we're always going to be checking, in this iteration, we're going to be checking the current Jth element to the next one, J plus 1. Okay, so at the end of this iteration, we will have completed all of our comparisons. Our so far clause, if I will be up to and including aj plus 1. So that's what we have characterized here. Okay, so this is saying after that iteration, in iteration J, remember I compared aj to J plus 1. So after that iteration, the maximum element of all of these elements, so the maximum so far, will be in the right position so far. This is where it belongs so far. So remember how that 7 floated its way up? Well, in the interior iterations, it was not all the way where it belonged yet, but it was basically as far as it could get so far, which is its position it belongs so far, which is the J plus 1. So I feel like we've characterized this correctly. So let's push forward with our proof then, and maybe not surprisingly, we're going to do our proof by induction on J. Okay, so J again being our iterator, the loop, and whenever we have a for loop, that's going to be the way we want to go. And so now what we want to do is do our base case, right? So our base case, we have to decide which J we want to choose. Now, remember, I think I pointed this out in our earlier videos on loop invariants, that usually we want to pick the iteration before our first iteration of our loop. We can actually pick the first iteration of the loop. Usually though, that is a more complicated instance. I usually shy away from that just because it means more work, more math, and more writing. And I'd rather do less work, less math, and less writing if I get a choice. So I'm instead going to pick before my loop. Now, usually, we can quickly go back here and see that my j here starts at 1. Right? So that means before my loop is going to be j0. Okay? So j equals 0 will be the beginning of our loop, or rather before the loop begins. So when I'm talking about after iteration 0, I'm actually meaning before the first loop, before the loop even begins. So what is it going to mean? Well, all we need to do is go and plug in our j into the rest of our expression up here and see what it's saying. It's saying the maximum element of the sequence starting at a1 but ending at, for j equals 0, 1. So the sequence is just only got a1 in it, is in position 1. So the maximum element of that sequence is just a1, and it is in position 1. Well, that's exactly what we need to argue. So that's all I have here. So that's, as I think I've pointed out before, sometimes our base case is so simple, we're just double checking what it is that needs to be true and then seeing, oh yeah, that's true. Okay, so in this case, all we needed to check that was true is that the maximum element of this list is in the right position. Well, it is. Okay, or another interesting way of saying that is that both the empty list is just trivially always sorted because there's nothing in it, and then so is a list with only one element in it. It can't be out of order, right? It's impossible. So this is trivially true, so we're done. We're just done our base case. And I'll maybe comment as well that in loop invariants, if you're seeing a proof of this online somewhere, you might see they left out the base case. And you might be like, oh my God, don't they know how induction works? Well, let's give them the benefit of the doubt. Hopefully they didn't make an error. Probably what they did is they maybe did what I do sometimes, to say, well, this is so obvious, this is very trivial, that I'm going to expect that most of my readers have already anticipated this, and let's just jump ahead to the crunchy part of the proof, the part that's maybe not trivial. But for our purposes today, this might not seem very trivial, so let's leave it in there, and that's what I've got there. Okay, so let's move on to our next step, which will be the inductive hypothesis, of course. So now here I'm talking about j. Now remember, what we're going to do now is talk about the next iteration, okay, j plus 1. So prior to iteration j plus 1 is what happens after iteration j. So I've really just copied this same business down here, right? Before we get started on j plus 1, we'll start out in the state that iteration j left us in. Iteration j left us in this state. We'll start out in this one. So what does that mean? In our inductive step, we now need to argue that after iteration j plus 1, we're in the state that we should be in. Now what that means is retranslating this statement here in terms of j plus 2. So really, we just get it with j plus 2 in here. We just need to argue that the maximum element of this expanded list, now that includes j plus 2, j plus 2, sorry, is in position j plus 2. Okay, now let's, again, come up high, abstract a little bit, take a bird's eye view. Where are we? Where do we need to go? Usually that's a good thing to do as you start out your inductive step, is saying, okay, where am I trying to get to? Okay, and that's what I've actually just iterated here. I'm saying, this is where we're trying to go. So what do we know? Well, what we know is whatever is stated for us in the inductive hypothesis, and maybe any other premises that we have started out with. But in this case, you usually want to marry these things together and find a middle ground between them, okay? So in this case, we know already that the maximum element out of all of these, so again, we were calling it so far, right? The maximum element so far of the first j plus 1 is sitting right here at the top. We need to show, after we're done this step, that the maximum element of all of them is now sitting in the top spot. So let's just consider in our mind for a second, there's two possibilities. The maximum element of all of these elements is either in position aj plus 1, because we know the maximum element of all these elements is in j plus 1, All the rest of them are less than it. So the maximum of these ones is either that one, right? If it was the 7 and it was floating up, it would be that one. Or it could be this new one that we've encountered. Remember, if that 7 was floating up but our list was really long, we might encounter an 8, right? And eventually we might get to an 8. So the idea here is that that maximum element that we're looking for is in only one of two positions. It's in this position or it's in this position. And that's the next step I'm going to say. We know by assumption that the maximum element of these ones is in position j plus 1. So either this is the maximum element of all of our elements, or aj plus 2 is. I think I said that in a slightly different way, but I like the way I've said it here on the slide better. Probably because I had time to sit and type it in and I picked something really elegant. Okay. Okay, so we got that far. Now what we say is, well, what do we do in this step? Well, guess what? We compare those two. And what do? This is the bubble sort cleverness. If they're out of order, we swap them. So in this iteration, we compare these two and swap them if they're out of order. So after this iteration, the maximum element out of all of them must be in the right position. And that's, again, the cleverness. Now, we sort of set up all this inductive machinery just to get to this one punchline. This is the clever bit. Okay, look, the maximum element used to be in position aj plus 1, or it might be the new element. After this step, it must be in position aj plus 2. And we're good, because that's where induction power sort of takes hold and carries on. It's going to say, oh, well, then if this works, then it's going to punch through to j plus 2 and j plus 3 all the way to the end, wherever we got. And that's the end. So by induction, we're done. By induction, we've argued that that maximum element so far has reached the position that we want it in so far. All right, let's see if we can take this one more step. Can we use this property? We're going to need to use this property to argue the outer loop invariant. Okay, so somewhere in the outer loop, we're going to be like, well, now we do the inner loop. Well, what happens after the inner loop? What do we know after the inner loop? It floats to the maximum element so far up to the right spot. And actually, in the outer loop, we're not going to be focused on the inner loop one at a time like we were here. We're done with that business. We've proven what it does one at a time. We now are going to say what it does after the last iteration, and that's the one that we really want, is the maximum element so far is really the maximum element of the whole list, and it's floated to the top. That's the kind of thing we want to argue next. Okay, so let's keep going. So let's see if we can reformalize that outer one. The outer one that we had before was something like the I maximum elements are in the I right positions. Now again, formalizing that means, okay, characterizing that exactly. What do we mean the I right positions, or what do we mean the I maximum elements? So let's see again. So the beginning of this is pretty standard. After iteration I, okay. Here I'm just identifying which loop because we have two of them. And here I've got that first clause, the I maximum elements, and a little bit of formalism we've added here is just saying the maximum elements of what? And of the whole list, actually. I could have just put A here, but I put A1 up to AN so that it reminds us, you know, these names that we're talking about, they have names, might as well use them, okay? And then also to emphasize that the I actually isn't showing up here. We mean the maximum elements of the whole list, not the maximum elements, say, so far, okay? The maximum elements of the whole list. So the I maximums are, and there's actually two pieces here. Maybe I should clarify. The first bit is in ascending order. So the I maximum elements of this list are in ascending order, and they're in the right position. So that's sort of two pieces of saying they're all where they belong. Okay, so they're in ascending order and they're in the right positions. What do I mean by right positions? Again, I formalized that here. They're in positions n minus I plus 1 up to n. Why do I have that? How do I know that that math is right, that n minus I plus 1? Well, sometimes the way I test that is I pick easy values of I and plug them in and see what happens. So the first iteration is iteration I, right? So it's saying n minus 1 plus 1. So that's n, the minus 1 and the plus 1 cancel out. So we just get n are in position n to n. That's only one position. And I guess since I was 1, it says the 1 maximum element is in position n. Hey, that's exactly what I want. Okay, so maybe now I test it for a different I just to make sure. And usually, why not 2? Okay, so the 2 maximum elements, so this math over here better work out right. We get n minus 2, but plus 1, that gives n minus 1, are in positions n minus 1 to n. Okay, that sounds like it's right. Okay, usually here, I will test one more time. I say, but what about the last one? Okay, well actually the last iteration we do, if you remember the pseudocode, was iteration n minus 1. Remember the last iteration we only compared the last one to the first one to the last one and we're done. So not the first one to the last one. I don't know what I was saying. We only do one comparison in that last iteration. But in that last iteration, what is the actual argument here? It's going to say, okay, after iteration n minus 1, the n minus 1 maximum elements, okay, I kind of like where this is going, but I'm not 100% yet, are in positions n minus 1 plus 1. What is n minus 1? That one you almost want to take to scratch, but I'll tell you what that comes out to. It's 2. So it comes out to 2 to 2n. Okay, well those are where the n minus 1 maximum elements should be. They should be in position 2 to n. Okay, and if you want to fill in a little gap of our final proof of correctness coming up here in a second, it is to say, well, where is the last element? That last element is the minimum element, and it's in position 1, and that's where it belongs to. So actually, all of the elements are in the right spot. Okay, so have we characterized the outer loop properly here? Well, I feel like it passes my inner intuitive tests. So let's see if we can argue it correct. And once again, we will conduct this proof by induction on n, or sorry, in this case on I. And again, we'll start out at the beginning, i.e. before the loop, which actually in this case is before the algorithm even begins. And that will be in our case, I equals 0. And again, let's just plug in I equals 0 and see what that says, folks. So first of all, it says the 0 maximum elements. So I'm going to just stop us right there. Whatever it's saying about the 0 maximum elements is true because, well, there could be a few false things you could say about the 0 maximum elements, like there are 10 of them. But in this case, remember what we're saying is the maximum elements are in the right position. That's what our clause kind of is saying. Well, if we're plugging in 0 there, we're saying the 0 maximum elements are in the right position. Well, of course that's true. Okay, and so really we're pretty much done. So I maybe emphasize that by saying they are in ascending order in no positions. Okay, and this is something that's true when we have sort of these absurdities like this, where we're saying in all the positions that start at n plus 1, but then end at n, well, there are none in that order because n plus 1 is greater than n, and it should be less than if we want any, or equal to. So again, this is another great example of a vacuous case, and again, as I mentioned in the inner loop, that you might see this sometimes left out by some people proving it, not because it's not necessary, not because it's not an important part of the inductive framework, but just because they might say, hey, that's obvious, and I think you think it's obvious too, so I'm going to leave it out so we don't waste each other's time. Well, I'm leaving it in because you might not see it as obvious, and we're trying to learn this inductive structure, so let's not skip any pieces while we're still learning it. Okay, so let's go to the next piece. So the next piece of the inductive hypothesis then is, the inductive hypothesis is the next piece. So let's take a look at the inductive hypothesis. Now remember, what the inductive hypothesis is intending us to do is it set us up for that next iteration. If this is what's true after iteration I, what's going to be true after iteration I plus 1? Okay, so after iteration I is what happens before iteration I plus 1. So I've just copied down the business up above here. So prior to iteration I plus 1, we're going to assume that this is true. You'll notice I've got the same business. And then we're going to try and argue what's true after iteration I plus 1. Now this one I want to be a little bit careful with. Okay, so let's go ahead and plug in to this same clause. We're going to be plugging in I plus 1. If prior to this iteration the I maximum elements are in the right positions, then after this iteration the I plus 1 maximum elements should be in ascending order. And now I need to be a little bit more careful here. What positions will they be in? Instead of I need to plug in I plus 1. And I need to be careful here. That minus applies to the I and the 1. So I get minus I minus 1. So the minus 1 and the plus 1 can't cancel out. So I actually get n minus I. Okay, n minus I. So I've just basically taken what we argued there and tried to place it down here a little bit again. I've got what we know. Okay, so by assumption we know the I maximum elements are already in the right position. Why am I pointing that out here? It's basically saying I don't need to argue this bit. This bit is already established. Before I got to this, even though it's one of the things I'm trying to argue all I plus 1 elements are in the right positions. I don't need to worry about these I. They're already in the right position. So what I really need to argue is just that the maximum element of these ones that are left gets moved into the position that it belongs in. Okay, so all the ones that are in the position that they belong in already, we're leaving them alone. But in this iteration, one more floats up to where it belongs. And that's going to be the maximum element of these remaining elements, and it's going to float up into position n minus I, which is the next available position before this one, n minus I plus 1. So, okay, so once again, a lot of this inductive framework is just to set us up for a coming punchline, okay? And this coming punchline is going to have to use the inner loop invariant that we've already proven. So let's try and do that, okay? So now we're going to leverage that inner loop invariant and say, well, what did it tell us? So let's go back and basically here I'm really just copying what it told us. It says, okay, the inner loop invariant told us that after iteration j, so again, I've probably just copied this down, of the inner loop, that the maximum elements of this chunk is going to be in position. So the maximum so far has floated up to the top, okay? In particular, which iteration do we do? Okay, iteration I plus 1 is the one we're currently in, right? Remember, we're arguing about I plus 1. So iteration I plus 1 is the one we're currently in. So how many of these loops do we do on the inner one? Okay, so we might have to go back and take a look at our pseudocode in there. But remember, our inner loop went to n minus I, okay? So if we're in iteration I plus 1, it would go to iteration n minus I minus 1. Again, remember the minus is going to hit both the I and the 1. So we get to this loop here. So up above here, when we were talking about what happens after iteration j, we can plug in this number n minus I minus 1 and see what happens. We're plugging that in for j. So we'll plug that in here. So instead we're going to get n minus I minus 1 plus 1 here. Oh, we see I've got it right here. The minus 1 and the plus 1 cancel out to give us just the n minus I that we're looking for. And which position will it be in? It will also be in position j plus 1, so plugging in this in for j plus 1 again, we get n minus I minus 1 plus 1, the plus 1 and the minus 1 cancel out again, we get the n minus I that we're looking for. So there's a lot of I plus 1s and j plus 1s and minus and so on going on here, but if you follow along with each of those comparisons that we did there as we went, all that this is saying is, this is the punchline that I was hinting at, is saying, hey, the inner loop, the way it works, we already proved the way it works, is that it's going to float the maximum element up to the top of this sublist. So after we let it run through and we stop it, we know that the maximum element that we're looking for has now floated up to the position it belongs in. And so which element is that? That is the element that belongs in n minus I. It's the I plus 1th maximum element, and it's floated up to its right position. So now that it's in its right position, couple that with what we already knew here, that the first I elements were already in the right position, and we're done. We can say, okay, now I plus 1 elements are in the right position, and that's what we wanted. So we're done. We're actually done the inductive step, and we're done, therefore, induction altogether. So at the end of this, we've argued that. So again, let's break this into the punchline of the final step. We're saying that since the in the inner loop, we float that maximum element so far up to the top of that inner sublist, that means in the outer loop, we have the I plus 1 maximum elements. Well, now let's put the final piece in our puzzle. We've built up 2 theorems just so we can get to the third theorem, which is bubble sort is correct. That's what we want to know, right? Bubble sort, this algorithm we were looking at, is correct for the sort problem. And so let's just do that. And usually the point of proving these loop invariants is so that this part is actually kind of easy. So hopefully this is, like I said, the last piece. It's like plugging the last piece in a puzzle. It should be the easiest piece, okay? So let's put the last piece together. So now that we've pushed our way all the way out, we're going to put ourselves in the proof of correctness kind of framework. We're just saying we want to make this general, so we're going to start by saying, give me any old input sequence, any sequence of integers of any size. Okay, that makes it arbitrary and that makes it general. Okay, then what we want to do, just like when we were applying the inner loop invariant in our punchline in our inductive proof, we want to apply the outer loop invariant as our punchline in the proof of correctness, which means it's the main piece that's going to put everything together or hold everything together. Okay, so we're going to bring it in usually into focus first. Okay, so here we're saying, what did the outer loop invariant tell us? It told us that after iteration I, that the I maximum elements were in the right place, in the I right positions, and specifically in these positions, n minus I plus 1 to n. Now remember, how many iterations did we do of the outer loop? We did, if we're not following, our notes aren't very clear, we might say we did n, but no, we actually did n minus 1. Remember, we stop at iteration n minus 1. So let's focus on that iteration. In particular, when the outer loop is done, what do we know? We know that after iteration n minus 1, not the n maximum elements, but the n minus 1 maximum elements are in ascending orders from position 2 to n. Remember, we kind of hand-wavy did this argument already, right? We said, what numbers would it be? It would be 2 to n. But the last piece I said is, but that means the last element that we haven't talked about in these n minus 1 maximum elements is the minimum element. And it's left alone in position 1. That's where it belongs. So it's right where it belongs. So sort of an interesting way of saying that is, if you put n minus 1 elements in the right position, the last element has to be in the right position because it's the only position left. So we're done here. Basically saying that after iteration n plus 1, we return a permutation of A that is in ascending order. Remember, that was the definition of the output in our sort problem that we started with at the beginning of this video. And I think that brings us to the end of this video. So in the next video, we'll do some runtime analysis, but that's it for this one. So thanks a lot for watching, and we'll see you in that next video.